Welcome everyone, this is Matteo Matteucci and I'm from Politecnico di Milano. Within this presentation I will continue my previous lecture on Federated Learning for Privacy-Preserving Machine Learning, which is delivered as part of the AI-SPRINT project. In the previous lecture we have introduced the idea of Federated Learning. We have explained why it is important to perform privacy-preserving learning. We have described the idea of a continuum of training between edge devices and cloud. Today we will look at a couple of advanced details on federated learning with respect to several dimensions. First of all, the network topology. We will divide between centralized, clustered, and fully decentralized federated learning. We will discuss about data availability, data partition, and at the end, we might even introduce some of the open source frameworks that exist nowadays. When we talk about network topology, we talk about the topology between the clients that compose a federated learning architecture. Remember, there is a centralized service and some of the clients that participate in the learning. When we talk about centralized federated learning, we assume that it exists such a server. It's trusted and will both manage and monitor the trading process. All clients that are our learning clients communicate directly with these central servers, and the servers performs the aggregation of the contribution. Remember, federated averaging, what the server was doing was sending the model to the client. Each client was performing a few steps of stochastic gradient descent, was sending back the parameters, the weights of the models, and the central server was aggregating these parameters. Sometimes what we have is a cluster of clients, where clients are clustered together according to their data distribution or some system constraint. Still, we have a trusted third party to monitor and manage the process, our centralized server. But now what happens is that each cluster of client will suggest the centralized servers how it's the best way to combine the model contribution. For instance, based on each of the cluster, the centralized server might weight each contribution to the model in a different way. Finally, we have a fully decentralized federated learning. In this case, we don't have a trusted third party which monitors and manages the learning process. What happens is that we have a peer-to-peer topology, no trusted third party, and a trusted peer-to-peer protocol substitute the role of the central servers. So what happens here is that the aggregation does not happen on the centralized server, but it happens on each client. Sometimes this is also backed up by a blockchain-based update ledger. Another dimension which characterizes different federated learning scenario is related to data availability. Remember about distributed machine learning and how this is different from federated learning. In distributed machine learning, the data is stored in a network of powerful cloud machines. Data can be shuffled and balanced across clients. Any client has access to any part of the dataset, and here the computation is the only bottleneck. It works pretty well, pretty efficiently, but it typically reaches a bottleneck of 1,000 clients, so you cannot scale above 1,000 clients. Then we have cross-silo federated learning. In this case, data is stored in edge devices with a high computational power. Think about institutions. The classical examples are, for instance, hospitals, where a silo is represented by a hospital. You have a lot of devices within the hospital. Data is stored at the hospital. It does not leave the hospital, and only the model is sent to a centralized server for merging. Here, differently from distributed machine learning, we have that data never leaves the client. Data can be accessed only by the owner of the data, and data samples are never shared with the centralized server. Here, what makes the bottleneck is either the computation or the communication. It typically scales up to 100 clients. Remember here, the client is an institution. Then we have the so-called cross-device federated learning. Data is stored at edge devices now, with low computational power, at end-user devices. Just an example, think about the Google keyboard that we have presented last lecture. Again, data never leaves the client, but now the client is a cell phone. Data can be accessed only by the owner, that is, by the cell phone, and only communication is the bottleneck because you have up to 10 to the 6 clients that participate in the computation. You see that, again, data availability becomes another dimension which can classify federated learning, which in the distributed machine learning framework is not federated anymore because data can be shuffled, but in the cross-silo is somehow in the middle between pure cross-device and pure distributed machine learning. Another dimension which classifies federated learning is data partition. We have horizontal federated learning when features overlap significantly between clients. So different clients have data and the features overlap significantly. What they have different are users, are samples. So basically what you might have as an example, you have the same service provider in different regions, and what differs are the end users of this service between the regions, but because they use the same service from the same providers, the features are the same. Here, what you get is generalization. What happens is that you have a model which is based on the same features, but can leverage more data by the federation of different regions. On the other end, we have vertical federated learning. Here, features overlap a little. What overlaps are samples. Think about two institutions like a bank and a store in the same regions. Here the features are different because the features which characterize the use of a bank and the features that characterize the use of a store are different, but the users are the same because in the same regions we have the same users. In this case, you cannot exchange the data regarding the user, so the two institutions, they agree on sharing data and labels regarding the use of their services, and they can improve their model. Finally, we have transfer learning. Transfer learning is probably the extreme of federated learning. Here, features overlap really a little, and also samples overlap a little. For instance, two different institutions in different regions. So, being different institutions, they don't share the features. Being in different regions, they don't share the samples, which in this case are the users. Here, what you do, you can transfer the model learned in one institution in a region and use its parameters in another regions for another institution. Classical federated learning is the first one, horizontal federated learning. Some cases exist about vertical federated learning. The last one is not so common in common practice. So let's go back for a minute to the general federated learning pipeline. We have a centralized server most of the time, either in a cross-silo or in a centralized federated learning, which initialize the model, send it to the clients. Then local clients could be single devices in a classical cross-devices federated learning, or could be institution in the cross-silo federated learning. They train their model and they send back the update to the server which updates the centralized model by combining the local updates. This can be done by simply averaging the contribution, but in the case you have clustered contribution, if you remember in the case of clustered federated learning, you can also weight differently the information coming from different clusters. Now, when things can go wrong? Well, if we take the classical federated averaging, it's very simple and easy to understand. It works well in practice, but sometimes it can diverge in a sense that it will not converge to a single model and the iterative process will not stop, especially if you have heterogeneous devices and heterogeneous dataset. So, for instance, if you have devices with data which are significantly different from each other, then this might turn out to be a critical aspect in federated learning. This is called statistical heterogeneity, and the model might not converge at the end of the training. This is something that has to be taken into account when deploying an algorithm that does federated averaging. Statistical heterogeneity is not just the only heterogeneity source that might affect federated averaging. Another one is system heterogeneity. Some devices might be more powerful than others. They might perform training faster than others. It means that they return their results to the centralized model earlier than others. These late devices or less powerful devices in the literature are called stragglers. When you have a high number of stragglers, it means that you have a high number of devices that deliver their contribution later than the other. This might lead again in an instability in training, and because of this, the training might not converge. Several improvements have been proposed to deal with statistical and system heterogeneity. One example is FedProx. FedProx is an improvement with respect to the classical federated averaging, which tries to deal with both statistical heterogeneity, so that it will use some smoothing factor to deal with that, and it will also try to cope with system heterogeneity so that you can have an incomplete update in the presence of stragglers. In case of statistical heterogeneity, the solution is very simple. Instead of just updating your loss function as you would usually do, you also try to discourage with the regularization term big changes in the weights. By discouraging big change, you reduce the instability of the system, and because of that, you improve convergence. Just as an example, if you remove this regularization term, you go back to federated averaging. So the FedProx algorithm is just a generalization of federated averaging. Another aspect that might be important to highlight is the communication cost of federated learning. If you remember, when making a distinction between centralized cross-silo federated learning and cross-device federated learning, we highlighted as cross-device federated learning having a high cost in communication. Because of this, different strategies have been introduced to reduce this cost. One of these is quantization. So for instance, by reducing the number of bits required to send the update to the server, and these reduce the overall cost of quantization. Another example is to reduce the number of parameters. So select and design small TinyML models to be trained in the federation. Finally, we could have importance-based update. So we don't send every time from every client all the weights, but we selectively send models weights using some sort of attention-based importance, and because of that, we only send those that we consider to be the most important. Another thing that might reduce the cost of communication is by exchanging less time the model parameters with a higher quality. What does it mean? It means that each of the client increases the local computation. By increasing the local computation, what happens is that the model will learn faster. We reduce the iteration of the averaging, although this might include some issues in convergence as well. With this, I have concluded also my second part of the Federated Learning for Privacy-Preserving Machine Learning lecture within the AI-SPRINT project.